The last day of the conference, so we'll start with a lecture by Thiago Fassarella from UFI, and we will discuss the moduli of Higgs bundle over the 5-puncture sphere.
So
Thiago,
thank you.
Please.
So thank you for the invitation, and thank you for coming. So let me start just by saying that this is a joint work with Frank O'Hay. So we look at Higgs bundles over the Riemann sphere minus 5 points, which means that they have some logarithmic points, poles in a finite set of points. So to begin with, let's denote, as usual, by P1, the complex projective line. And we fix a subset of 5 distinct points on it, which we call parabolic points. Then we can, first we can construct the representation varied of the fundamental group of the puncture line, which is formed by homomorphisms of the fundamental group in SL2 with some conjugacy, fixed conjugacy class at the punctures. So gamma I means a loop around a parabolic point. Then this is a well-known and classical object, which, as I mentioned, is called the character varied or the Betti modular space. So it follows from the non-abelian hard theory that the representation varied is admits actually an avatar, which means that these modular spaces have the same underlying topological space, which is a modular space of Higgs bundles, which is the main topic of my talk. And by a Higgs bundle, I mean, so let me write down here the definition. So a Higgs bundle is a pair consisting of a vector bundle E and a homomorphism, a traceless actual homomorphism of the vector bundle with coefficients on the sheaf of 1 forms with poles on lambda, on the set of 5 points. So this is a 2x2 matrix of 1 forms with poles on lambda. Then I would like to emphasize that the former modular space is a topological object, which means that it depends only on the topology of the puncture line. But the second modular space depends on the algebraic structure of the puncture line. Okay. So this leads to the investigation of algebraic invariants, such as the Hitching vibration. So the Hitching map is a map from our modular space of Higgs bundles to the space of quadratic differentials, which takes a Higgs field and sends to a quadratic differential by just taking the determinant of the Higgs field. So the Hitching map is just the determinant. It's the map from our modular space to the space of quadratic differentials, which is an affine space in this case. So in our specific case, actually, it is a two-dimensional vector space. So this map has an amazing property, which is the following. The general fiber of the Hitching map is an abelian variety. Which is isomorphic to the Jacobian variety of the spectral curve. So I will go back to this point later on this talk. Let me just. This is the Jacobian of the spectral curve. But singular fibers of the Hitching map are, in general, are difficult to deal with. So the first goal of this talk is to describe the singular fibers of this map. Okay. So among those singular fibers, there is also a specific fiber which is called the nilpotent cone, which is the fiber over 0. And this fiber contains the fixed locus of the C star action, which means the multiplication by a non-zero complex number on the Higgs field. So we have an action of C star just by taking the multiplication in the Higgs field. Okay, so before going through the technical part of the talk, I just would like to say that we were motivated by the following guess of Simpson. So Simpson, in his paper, an explicit view of the Hitching fibration on the bad side for P1 minus 5 points, he writes, one therefore guess that the degenerate fiber of the Hitching fibration should look like elliptic curves times degenerate elliptic curves, where the degenerate factor has two irreducible components in this way. So Simpson believes that the singular fiber of the Hitching map is a kind of product of an elliptic curve times to a degenerate elliptic curve. So by a degenerate elliptic curve, he means two copies of P1 intersecting in two distinct points in this way. Okay. Yes, yes, right. So the fiber should look like those fibers should look like something like this. So it should have two irreducible distinct components in this way. Okay, so let me introduce our modular spaces of parabolic vector bundles and parabolic Higgs bundles. So let's fix a Riemann surface, let's say S, and a bound of points which will define a divisor on this Riemann surface. Then a rank 2 parabolic vector bundle is just a pair consisting of a vector bundle, E, vector bundle E, this is the projectivization of the vector bundle. And for each fiber over a parabolic point, we take a one-dimensional subspace in this fiber. Okay. Okay, so a parabolic Higgs bundle, in order to have a parabolic Higgs bundle, we add a Higgs field, which is a traceless homomorphism with coefficients on the sheaf of one forms with poles on D, and we ask the Higgs field to be nilpotent with respect to the parabolic direction, which means that the residual matrix satisfies these conditions. Okay. So the Higgs field, it must respect the parabolic direction on each fiber. Okay, so now, in order to have a good moduli space of parabolic vector bundles and parabolic Higgs bundles, we need to introduce a notion of stability which depends on the weight vector, which we call A, which is just a sequence of real numbers between 0 and 1. And then we say that a parabolic vector bundle is semi-stable with respect to the weight vector if for every line subbundle L of E, then the difference between the slope of L minus the slope of E minus the slope of L is non-negative. So as usual, the slope is the parabolic degree of the vector bundle divided by the rank. So this gives us a notion of stability, and in order to have a semi-stable parabolic Higgs bundle, we do the same, but in this case, the difference between the slope is computed just using invariant line bundles under the Higgs field. So the definition is the same, but we consider invariant line subbundles of E. Now, for each fixed integer D, then there are moduli space of a semi-stable parabolic vector bundles and parabolic Higgs bundles of degree D. And then it's known that in our specific case, when we fix the projective line, the divisor of 5 points, and we take the weight vector having a half as coordinates, the degree is 0, then the moduli space of parabolic vector bundles is a Del-Pezzo surface of degree 4. So we can, in this picture, we then have another moduli space in a map, which is actually a rational map, which is obtained by forgetting the Higgs field. Okay, so we take a Higgs field, and then if we forget, we take the Higgs bundle, and then we forget the Higgs field, we get, again, a parabolic vector bundle. And this is a surface, which is actually Del-Pezzo surface of degree 4. So it is the blowing up of P2 in 5 distinct points. Yes, because the stability condition, it depends. For instance, you can have a Higgs field which is irreducible, which means that it does not have any invariant line bundle. But the underlying parabolic vector bundle can be unstable in this way. So my goal in this talk is to, first, is to complete this picture. Okay? Is to describe all the fibers of the Hitching map. Now, to understand the singular fibers of the Hitching map, we need a notion of symmetries of this modular space. So we need to introduce some symmetries which are given by elementary transformation, which will give us the automorphisms of this modular space. So the elementary transformations will gives us a notion of symmetry. So what I mean by an elementary transformation, it is a correspondence between parabolic vector bundles. So from the point of view of Rayleigh surface, here I'm looking at the projectivization of the vector bundle. So it corresponds just to a flip, which means that we take a parabolic direction, then we can blow up this point. Then by doing this, there was a zero self-intersection curve, which is a fiber, which is now a -1 curve. Then it can be contracted to a new Rayleigh surface. And we then obtain a new parabolic direction in this way, which is the point obtained by the contraction of this curve. Okay. From the point of view of vector bundles, the transform vector bundle is just the subsheaf of E, whose sections are those sections of E passing through the parabolic direction. Okay. So this notion of symmetry gives a map between moduli spaces of parabolic vector bundles, and this gives us a correspondence between moduli spaces of parabolic vector bundles with an appropriate modification of weights, because we need to preserve the stability condition. And finally, we can do the same for Higgs fields just by taking the restriction of the Higgs fields to the transform vector bundle E prime. Okay, so there is also a symmetries of our moduli space of vector bundles. And then I'm going to use this notion in order to understand the singular fibers of the Hitching map. So let me note that at this point, let me note that if the weight vector has a half as coordinates, for instance, if it is the central point, then the set of elementary transformations induce automorphisms of the Darlow-Puzo surface, because the weight vector does not change when we do an elementary transformation in this way. And it turns out that the group of elementary transformation, the group generated by those transformations, coincides with the whole automorphism group of the Darlow-Puzo surface, which is known to be a finite group of order 60. Okay, so so what? Okay, so as I mentioned, my goal is to describe all fibers of the Hitching map. Then we will start with the simple case, which is the generic fiber. And to understand the generic fiber of the Hitching map, we need to discuss the notion of a spectral curve. So what I mean by a spectral curve, so we fix a point on the Hitching basis, which comes from the determinant of a Higgs field. Then we just locally we take the curve defined by this equation. Then we see that if the determinant has a 0 of order 2, then this curve has a ramification point over our case curve x. So the picture should look like something like this. So it is a curve which the genus can be computed by this formula. And by the condition to be nilpotent, we have at least one ramification point for each parabolic point, and there can have other extra ramification point, but this is a 2-by-1 map over our case curve x, which have some ramification points. And if we going back to our specific case, we get in general, a genus 2 curve over P1. So the spectral curve depends on this point, which we can fix. We can think at the general point. So we can think this space of quadratic differential as the space of the spectral curves. So in general, if you take a general point, the general spectral curve will be a genus 2 curve over P1, which ramifies over 6 points. 5 of them are the parabolic points. And a singular spectral curve happens when the extra point coincides with one of the 5 parabolic points. So there is a locus of singular spectral curve, which is a set of 5 lines, which lies in the space of quadratic differentials. So this is the locus of singular spectral curves. And we can even try, we can try do something different. Instead of considering the curve of eigenvalues of the Higgs field, we could consider the curve of eigenvectors. So the curve of eigenvectors lies inside our Rowland surface. And by the condition to be nilpotent, this implies that the curve of eigenvalues of eigenvectors has one ramification point over each parabolic point, parabolic direction. Then at this point, you may wonder if the spectral curve might coincides with the curve of eigenvectors. So this is the first guess we have. But actually, they can be different. Because, for instance, when the Higgs field is holomorphic at a point, a parabolic point, then we can check that the curve of eigenvectors has two distinct directions in this way, while the curve of eigenvalues has just one singular point. Anyway, we can take advantage of this construction in the following way. So instead of considering the projectivization of the eigenvectors, we can consider the whole fiber, the whole eigenvector, in order to construct a line bundle over the spectral curve. So as I mentioned, a point S corresponds to a spectral curve XS, which is a genus 2 curve over P1. And if you give me a point on the spectral curve, it corresponds to an eigenvalue of the Higgs field. Then we can associate to this point the corresponding eigendirection in this way. So what we get is a line bundle on the spectral curve, which I call M theta. Yes. And this gives us a correspondence between pairs given by Higgs bundles and line bundles on the spectral curve. But since all the Higgs bundles in the same fiber, or in the same Hitching fiber, have the same spectral curve. By definition, they have the same spectral curve. Then this gives us a correspondence between the fiber of the Hitching map and the Jacobian variety of the spectral curve. So this is the idea to obtain this isomorphism. Okay. Yes.
So why do these 5 lines meet in a point? What does that point mean?
Yes, this is the zero of the vector space.
Ah, okay.
Yes. So here, the fiber over this point is, it tends to be the most complicated one, which is the nilpotent cone. So now I'm just describing the general fiber. Then we'll try to understand the singular fiber, and then the nilpotent cone. So just one remark. As I said, if the spectral curve has a nodal point, if it is singular at this point, we have one eigenvalue, but we have two eigendirections associated to this point. So instead of obtaining a line bundle on the spectral curve, we obtain a torsion-free sheaf of rank 1. Okay. So the correspondence in this case, where the spectral curve is singular, is the following. We take a pair, and then this pair corresponds to a torsion-free sheaf of rank 1 on the singular spectral curve. And if the spectral curve is a smooth curve, then this is an isomorphism. I mean, for each pair, we obtain exactly one line bundle on the spectral curve. But here it's important to note that our modular space, we are considering also the parabolic direction. And in this case where the Higgs field, the fiber is smooth, then this map is an isomorphism. So the fiber of the Hitching map, in our case, our modular space of parabolic vector bundle, where we are considering the parabolic direction, the fiber is isomorphic to the Jacobian variety of the spectral curve. So it should be just the Jacobian variety, not the compactified Jacobian variety. And if the fiber, if the singular curve is, if the spectral curve is singular, then we show that this map, by forgetting the parabolic direction, corresponds to a blowing up, to a contraction. So the pairs of vector bundles are in correspondence with the compactified Jacobian variety of the nodal curve, and the fiber of the Hitching map, which sits in our modular space of parabolic vector bundle, corresponds to a contraction. By contracting the parabolic direction, then there will be two components. One component corresponds to Higgs field, which are holomorphic at the parabolic direction, and the other component is a desingularization of the compactified Jacobian variety. So why these components are isomorphic between them? Because we have a notion of symmetries in this modular space. And the elementary transformation gives us an automorphism of the modular space, and it sends one component of the Hitching fiber to the other component of the Hitching fiber. So this shows that these two components are isomorphic between them, and actually it is the singularization of the compactified Jacobian variety. So this is our first result. If the spectral curve has a nodal singularity, then the corresponding fiber has two components which are isomorphic to the singularization of the compactified Jacobian variety. So this confirms the Hitching gas, and the whole fiber looks like an elliptic curve times the degenerate elliptic curve, but it is actually, it is not a product, because the way in which both rollings intersect each other, actually it is explained by the elementary transformation. So this is like a twisted product, depending on the action of the elementary transformation. Okay. So there is a missing fiber, as I mentioned. The fiber over 0, which is now the nilpotent cone. So it tends to be the most complicated one. And one easy remark is that the modular space of bundles is one component of the nilpotent cone, because we can take the Higgs field to be 0. So the fiber over 0 has one component, which is S, by taking the Higgs field to be 0. And here there is a beautiful geometry, because, as you know, the del pizzo surface has 16 rational minus-one curves, and we might show that for each rational curve, each minus-one rational curve on S, there is another component of the nilpotent cone and then each one of these components has exactly one isolated point with respect to the C star action. So this picture describes the nilpotent cone, and also the fixed points with respect to the C star action. So the C star action is just the multiplication on Higgs field by a non-zero complex number. Okay, so I have, I think, 4 minutes, so let me say some words about the foliation conjecture. Okay. Okay, so now we add another modular space in our picture, which is the modular space of connections with SL2 logarithmic connections over P1 with the polar divisor lambda. And then it follows from the work of Simpson that each connection has a unique limit on the modular space of Higgs bundles. So the modular space of connections then there is a map by taking the limit when C goes to 0. And this leads to a decomposition of the modular space of connections by assuming that 2 points are equivalent if their limits are the same. So this decomposition are actually fibers of this map. And the foliation conjecture predicts that this decomposition forms a regular foliation of our modular space of connections. And conjecture has been proved by Loret, Saito, and Simpson for P1 minus 4 points in generic weights, and recently by Hu, Wang, and Zhang deal with 5 points and a weight vector satisfying this condition. And in our specific case, we take the central weight vector, then using this description of the fixed points with respect to the C star action, we may show that this conjecture is true in this specific case. So let me just give you an idea of the proof. So let P the non-separated scheme of undecomposable parabolic points. Then we have a map from the connection to this modular space of undecomposable parabolic points, just forgetting the connection. Okay. So this map induces we show that this map induces a regular foliation on the modular space of connections in this way. And finally, the description of the fixed points with respect to the C star action allows us to show that the Simpson decomposition actually it coincides with the foliation, the regular foliation defined by this map. So this is the idea of the proof. And okay, so I think I'll stop here.